Lecture video on rational functions. So to start off today, let's just define what a rational function is, talk about what they look like. So if p of x and q of x are polynomials, then the function of the form f of x equals p of x divided by q of x is called a rational function. You might recall the word rational back in rational numbers referred to fractions. So a rational function is simply a function that is a fraction. And this function will be fine provided that q of x is not the zero polynomial. In other words, we can't divide by 0, so q of x can't always be 0. So what is the domain of a polynomial function? So we spent this whole chapter looking at polynomials, so hopefully by now we've got the idea that the domain of a polynomial function is all real numbers, negative infinity to infinity. Now, if you divide a real number by a real number, the quotient is what type of number? So if you divide up a real number by a real number, what type of number do you get as the result? And the answer to that is a real number provided that the denominator does not equal 0. So we're fine when we talk about these things as long as the denominator doesn't equal 0. So based on that, if we look at a polynomial rational function that looks like this, the domain should be all real numbers except when the bottom is equal to 0. So we take the bottom, x squared minus 16 equals 0, and we solve for x. So add 16 to both sides. So x squared equals 16, and then we can use the square root property, so x equals plus or minus the square root of 16, which is 4. So the domain of this is everything except for negative 4 and 4. So one way to write that would be negative infinity to negative 4, union negative 4 to 4, union 4 to infinity. And so the question is, what happens at negative 4 and 4? So if we graph this, we can see. So y equals fraction. X squared minus 3x minus 4 divided by x squared minus 16. Okay, and so what we should notice here is that at negative 4, something odd is happening. What we're getting is the graph on one side of negative 4, the graph goes down significantly, and on the other side it goes up significantly, and we get really close to that. The other thing we should notice is at 4, it doesn't appear that anything's happening, and we'll look at what's actually happening there in a second. And then also notice as the graph goes to infinity and negative infinity, we get these horizontal, it looks like the graph is getting very close to horizontal. So we could go ahead and graph this in our notes. So what's happening at negative 4 is what's called an asymptote. So at negative 4, the graph gets really, really close to this line, but it never quite gets there. Okay. And then as the graph goes to infinity, there's actually another asymptote at 1 that the graph approaches but never actually gets to. And so then we can add in a couple other things that are happening here. So if we could get some ordered pairs. So let's just go back and look at the graph here for a second. So like, for example, we know negative 1, 0 is the x-intercept. You could click on the graph and try to find some other points. So like at negative 3, it looks like we're getting negative 2. Okay, so I'll just add those points. So I've got -3, -2. -1, 0. And so we can start drawing this graph. Now the interesting thing that happens at 4 is we actually get a hole in the graph. Because we know that's not in the domain, but as we could see in the graph that we just saw in the calculator, there is no asymptote there. And the reason that happens is because if I factor this polynomial, I can factor the top by finding two numbers that multiply to get -4 and add to get 3, and the answer is x minus 4 and x plus 1. And I can factor the bottom by using the difference of squares, so that's x minus 4 times x plus 4. And so what you should notice is these cancel out. So that means we can't plug -4 into the original graph, but it doesn't really affect what the graph looks like. So that's why we get a hole in the graph there. And then the other piece should look something like this. Okay, and so what you can see is when we can't cancel out something that's not in the domain, we get an asymptote, a vertical asymptote here. And if we can cancel it out, then we just get a hole in the graph. And then also that as x goes to infinity or negative infinity, these graphs kind of flatten out. So we think there's a horizontal asymptote there. So let's define what those things mean now. So an asymptote is a line that the graph approaches as... Oh, sorry, I can be more specific than that. A vertical asymptote is a line that the graph approaches as y goes to infinity or y goes to negative infinity, and a horizontal asymptote, and that P is not a typo, that's in the word, and oblique asymptotes are lines that the graph approaches as x goes to infinity or x goes to negative infinity. We also can call oblique asymptotes slant asymptotes. So the question is, how do we figure out where all these lines are? And so that's what we're going to talk about now. So if let f of x equal p of x over q of x be a rational function in lowest terms. So notice this stuff only works once we've reduced any fractions, which is what we noticed on the last page, right? For the one where it doesn't cancel out, we get an asymptote, but where it did cancel out, we just get a hole in the graph. The graph of f has a vertical asymptote corresponding to each root of q of x equals 0. So basically set the denominator equal to 0 and solve. If the and then that's how we find vertical asymptotes. And then the horizontal or oblique asymptotes are based on the degrees of the polynomials. So if the degree of p of x is less than the degree of q of x, so the degree of the top is less than the degree of the bottom, then the x-axis, which is the line y equals 0, is a horizontal asymptote. If the degree of p of x is equal to the degree of q of x, then the horizontal asymptote is determined by the ratio of the leading coefficients. So we're going to divide the leading coefficient of the top, or even you could take the leading term of the top divided by the leading term of the bottom to find the horizontal asymptote. And if the degree of the top, p of x, is greater than the degree of the bottom, q of x, then we use division to rewrite the function as quotient plus remainder divided by divisor, and the graph of the equation formed by setting y equal to the quotient is an asymptote. So basically the idea is we get y equals the quotient plus the remainder over the divisor. And then this part is our slant asymptote. Okay, so let's just go ahead and run through some examples of this. So a good idea, if possible, is always try to factor. So we can start by doing that here. So the bottom we can factor as We need to get two numbers that multiply together to get 6 and add to get -5. So our options for that are -1 plus -6, which is -7, and -2 plus -3, which is -5. So this is the one that works. So that's x minus 2 times x minus 3. And so look, in this case, we can cancel out an x minus 2. So this just ends up being 1 over x minus 3. Okay, so that means to find the vertical asymptote, we set the denominator equal to 0 and solve. So the vertical line x equals 3 is a vertical asymptote. And then to find horizontal or oblique asymptotes, we compare the degrees of the top and the bottom. So the degree of p of x and the degree of q of x. So in this case, the degree of p of x, well, there are no x's on top, so its degree is 0. This is x to the first power on the bottom, so its degree is 1. So in this case, the degree of p of x is less than the degree of q of x. So that means that the x-axis, or which is y equals 0, is the horizontal asymptote. And if we graph this function, we can see that that's what's happened. So we're going to do x minus 2 divided by x squared minus 5x plus 6. And so if we see, we can see it that at approximately 3, we get a vertical asymptote, and that the x-axis appears to be the horizontal asymptote, that the graph, as x goes to the right forever or the left forever, the graph gets really, really close to the x-axis. Okay, so there's one example. So let's try another example. In this one, there's no real way to factor either of these, so this is what we want to work with, so we can leave it alone. So to find the vertical asymptote, we set the denominator equal to 0. Subtract 5 from both sides, and we get x equals -5 as a vertical asymptote. And then for horizontal or oblique, once again, we compare the degrees. So the degree of p of x, and we compare that to the degree of q of x. So the degree of p of x is 1, because the highest power on an x here is x to the first power, which is the same as the degree on the bottom, which is also 1. So now when the degrees are the same, our horizontal asymptote is going to be y equals the leading term of the top divided by the leading term of the bottom. And the leading term of the top is -2x, because that has the highest power, right, on the top. And on the bottom, the term with the highest power is x, the highest exponent. So we simplify that, x divided by x cancels, and we get y equals -2. Okay, so there's two examples. So we got vertical asymptote was the same each time, and then we looked at two different ways to find the horizontal asymptote. And then let's do one that has a, then we'll look at one more that has an oblique asymptote. So this is, we can't reduce that at all. So we start by finding the vertical asymptote by setting x minus 9 equal to 0. Add 9 to both sides, and you get x equals 9. Then for horizontal asymptotes or oblique asymptotes, we look at the degree of p of x compared to the degree of q of x. So the degree of p of x here is 2 because it's x to the second power. The degree on the bottom is 1 because it's x to the first power, so 2 is greater than 1. So that means we're going to have an oblique asymptote, and we find that oblique asymptote by doing division. So in this case, we could use synthetic division. So this is our c, right? The number that goes in the box is the opposite of x minus 9, so that would be positive 9. And then the coefficients on x squared are 1 for the x squared term. There is no x term, so that's a 0. And there is no x constant term, so that gets a 0. And then we can do synthetic division. So 1 plus nothing is 1. 9 times 1 is 9. 0 plus 9 is 9. 9 times 9 is 81. 0 plus 81 is 81. So we could rewrite this as x plus 9 plus 81 over x minus 9. Sorry, not 8 minus 9, x minus 9. So quotient plus remainder over the divisor, which is this x minus 9 that we started with at the beginning. And so our oblique asymptote ends up being y equals x plus 9. Because as x gets bigger and bigger and bigger, this thing, the piece over here, the remainder divided by divisor, is going, as x goes to infinity, that piece is going to approach, a piece will approach 0. Because you're going to get 81 divided by really, really, really big numbers. And a number divided by a gigantic number is basically 0. And so as x goes to infinity, the graph will get really, really close to this oblique asymptote. So that's the idea. So what I'd like you to do is, just like we've done, take a moment, pause the video, and try this problem here on page 31, and then also these two problems on page 32. When you're ready, unpause the video, and we'll try these together. Okay, so now that you've had a chance to try these on your own, let's go ahead and walk through them together. So start by finding the vertical asymptotes. So we set the denominator equal to 0 and solve, add 9 to both sides. You get x squared equals 9. Use the square root property to get x equals plus or minus the square root of 9. So x equals plus or minus 3. So this one has two vertical asymptotes, x equals 3 and x equals negative 3. Then define the horizontal asymptote or oblique asymptote. You compare the degrees, so the degree of p of x and the degree of q of x. The degree of the top is x to the first power, so that's a 1. The degree of the bottom is x squared, so that's a 2. 1 is less than 2, so this has the x-axis, which is y equals 0, as its horizontal asymptote, because the degree of the top is greater than the degree of the bottom. And like I said earlier, feel free to check your answers using the Class Calc app, or you can try using the Class Calc app to find your answers. Okay, then on the next page, same idea. So I start by doing x minus 1 equals 0 to find the vertical asymptote. Add 1 to both sides, and we get x equals 1 for our vertical asymptote. For the horizontal asymptote or oblique asymptote, we find the degree of the top and the degree of the bottom. So the degree of the top is 1 because it's 3x, which is x to the first power, and the bottom it's 1 because it's x, which is x to the first power. So those are the same. So our horizontal asymptote will be equal to the leading term of the top, which is 3x, divided by the leading term of the bottom, which is x. 3x divided by x is 3. So y equals 3 is our horizontal asymptote. And last but not least, this one down here, find the vertical asymptote by setting the denominator equal to 0. So we subtract x plus 1 equals 0. Subtract 1 from both sides, and we get x equals negative 1. Then define the horizontal asymptote or oblique asymptote. We look at the degrees. So the degree of p of x and the degree of q of x. So the degree of p of x here is 2. The degree of q of x is 1. 2 is greater than 1. So that means that we have an oblique asymptote and we need to do division. So the opposite of plus 1 is negative 1. So negative 1 goes in the box. Our x squared term has a coefficient of 3. There is no x term, so that gets a coefficient of 0. And our constant term is 4. And then do synthetic division. So 3 plus nothing is 3. Negative 1 times 3 is negative 3. 0 plus negative 3 is negative 3. Negative 1 times negative 3 is 3. 4 plus 3 is 7. So this would be y equals 3x minus 3 plus 7 over x plus 1. And our oblique asymptote is this first part. So that's how you find asymptotes. So now what we can do is we can take this idea of limit that we talked about in the last section and apply it to these problems. So the key here is, as x approaches something, we're going to be getting we're going to be getting whole number answers as x goes to infinity because we're going to get near our horizontal asymptote. And as we approach certain numbers, we're actually going to get positive or negative infinity because we're going to approach the vertical asymptotes. So if we look at the graph of the first one here, so 3x squared minus 1 over x squared minus x. And we can see as x goes to infinity, so if you look at the right-hand side of the graph, this is obviously getting close to some number greater than 1. And the same thing happens over here. And if you click and drag on it, you can see that that number is, right now it's 2.912, and it's getting a little bit bigger. And if I go to the other side, I can see that it's 3.12114 right now, and it's getting a little bit smaller as I move to the right. So if we put those two pieces of information together, the fact that the left side is going up from 2 point something, and the one on the right is going down from 3 point something, those should meet at 3. So this limit is 3. We can also notice that the degrees here are the same, which means our horizontal asymptote is at y equals 3x squared divided by x squared, which is y equals 3. And notice that matches up here. So the limit as x goes to infinity will equal the horizontal asymptote. So you can either get that from the graph, or you can get it from using what we just talked about on the previous page to find horizontal asymptotes. For the second one here, what you should notice is there's a little bit of interesting notation here. It says x arrow 1 with a plus sign as an exponent. So what that means is x approaches a with a plus means we're looking at the right side of a. And if I had x approaches a with a negative, that means look at the left side of a. So if I graph 2 over x minus 1, two divided by x minus 1, you can see on the right-hand side here, to the right of 1, the graph goes up, and it'll go up forever. So that would mean that this limit is positive infinity. Whereas if I did the same thing, except instead of a plus, I put a minus sign there, we can see on the left-hand side of 1 over here, this piece that goes down, it goes down forever. So that means that that's going to have a limit of negative infinity. Okay, so that's the idea. So why don't you guys go ahead and draw a couple, go ahead and take a couple minutes, pause the video, and try finding these other two limits. Okay, so if you look at this one, if you were to graph this first one, what you would see is that on one side, as you go, let the x's get really, really big or really, really small. On one side, the x's will be getting close, will be negative 2 point something, and be going down towards negative 3. And on the other side, they'll be negative 3 point something, and they'll be going up towards negative 3. And so this limit is negative 3. And so we can also see that by taking the leading term of the top divided by the leading term of the bottom. Negative 3x divided by x, which is y equals negative 3. Okay, and if you look at this one, on the left-hand side, the graph should be going up. So that should be infinity. In fact, I'll go ahead and just draw that one. So negative 1 divided by x plus 2. And yeah, you can see on the left-hand side, the graph goes up forever. So that would have a limit of positive infinity. Okay, so that's the idea of how limits can be applied with rational functions. Now we can use all of this to help us figure out which graphs are which when you look at them. So if we go ahead and look at a couple of these real quick here. we could decide which one these are. So let's just go down the ones on the left together, and then I'll have you guys pause the video and try the ones on the right. So what you should be able to see by looking at this first one is that it has a vertical asymptote at x equals 0, right? Because we set the denominator equal to 0. And you should also be able to see that the degree of the top is less than the degree of the bottom, right? The degree of the top is 0, the degree of the bottom is 1. So whenever that happens, that means it has a horizontal asymptote at y equals 0. So what you want to do is go down, look at our graphs, and find the one where the vertical asymptote and the horizontal asymptote are at 0. And the only one where that happens is E. So this is E. Okay. For the second one here, we can see that we set the denominator equal to 0, add 3 to both sides, and we get x equals 3 for a vertical asymptote. So already that leaves me with A has a vertical asymptote at 3, B has a vertical asymptote at 3, D has a vertical asymptote at 3. And so that G has a vertical asymptote at 3. So it's one of those 4. And then if you look here, the degrees of the top and the bottom are the same, so our horizontal asymptote is going to be x divided by x, which is 1. So if we go and we look and we find the one that has a horizontal asymptote at 1 to go along with a vertical asymptote at 3, the only one that does that is A. Okay. For the next one, set the denominator equal to 0, so x squared minus 3x equals 0. Factor out an x and set those both equal to 0. And you get x equals 0 or x equals 3. So we need one that has vertical asymptotes at 3 and at 0. And the only one that has that is B. But if you wanted another little piece to go along with this, the degree of the top is less than the degree of the bottom. So that means y equals 0 is our vertical asymptote, which is what we see in B. And for the last one, we can see that x equals 0 is our vertical asymptote. But then notice that we have a the degree of the top is greater than the degree of the bottom, so that means I need a divide. So if we do division here, I'm not subtracting anything on the bottom, so 0 goes in my box. And then my coefficients for the top are 1, 0, negative 3. And so that means 1 plus nothing is 1. 0 times 1 is 0. 0 plus 0 is 0. 0 times 0 is 0. Negative 3 plus 0 is negative 3. And so we get x plus negative 3 over x. And so what we're looking for is y equals x. So that's a slope of positive 1. So it has to be one of the two with an oblique asymptote, and the one with a positive slope is C. So that one's C. So go ahead and pause the video for a second and see if you can match the other 4 equations to the other 4 graphs. Okay, so now that you've had a chance to try those, let's walk through them fairly quickly here. So set the denominator equal to 0, add 3 to both sides, and so we get x equals 3. And then the degree of the top is less than the degree of the bottom, so y equals 0 is the horizontal asymptote, sorry. So the graph with a horizontal asymptote at y equals 0 and a vertical asymptote at 3 is D. For the next one, set the denominator equal to 0. So we're looking for a vertical asymptote at 0. And then the degrees are the same, so we divide the leading coefficient. So y equals x divided by x, so y equals 1. So we're looking for one with a vertical asymptote at 0 and a horizontal asymptote at 1. And if we look, that should be down here, H. Okay, it has a horizontal asymptote at 1, that's the dotted line, and a vertical asymptote at 0, which is the y-axis. For the next one, set x squared minus 9 equal to 0. Add 9 to both sides to get x squared equals 9. Use the square root property to get x equals plus or minus 3. So the one that has vertical asymptotes at plus and minus 3 is G. And then last but not least, all we're left with is F. So this last one is F. Okay, so that's the idea for matching graphs and equation using asymptotes. So now the next thing we'd like to be able to do is we'd like to be able to do very similar to what we've done previously, which is solve inequalities using graphs of these things. So now that we've talked about the graphs, we can solve inequalities that go along with them. So remember, the idea here is we've got our graph, and we've got anywhere that the graph is above the x-axis, that's greater than 0. On the x-axis is equal to 0, and below the x-axis is less than 0. So in this first example, we're doing greater than or equal to 0, so we're looking for above or equal to the x-axis. So what we can do is we can graph this. So if we graph x squared plus 2x plus 1 over x squared minus 2x minus 15. Okay, there's a few things we want to note here. One is that we've got an x-intercept at -1, 0. We can also see that as x gets close to -3, we've got a vertical asymptote, right? This on the left-hand side, the x's are getting close to -3 and getting smaller. On the right-hand side, the -2 point somethings are getting bigger, so going towards -3. And then we can also see that we get a vertical asymptote at 5, right? This one, as we go down, we get close to 5, we get 4 point something, and it's increasing. And over here on the right-hand side, we get 5 point something, and it's going down. So we can transfer that over to our graph here. So we had a vertical asymptote at -3. We've got a vertical asymptote at +5, and we had a an x-intercept, at -1, 0. So right here at -1, 0. So the graph looks something like this. Okay. So now what we're looking for are the pieces of the graph that are above the x-axis or where it's on the x-axis. So this piece on the left-hand side to the left of -3 is above the x-axis. So that's -infinity to -3. Notice I use a parenthesis at -3 because there is no value of the function at -3. So that'll get a parenthesis no matter what. Even though we're doing or equal to, and we're used to that meaning that's a bracket, -3 cannot be a solution because it's an asymptote. So I use a parenthesis. Now, the weird thing that happens, now I also get from 5 to infinity, right? This piece over here on the right-hand side, this piece, is above the x-axis, so that's 5 to infinity. But then I also get a 1 point where it's on the x-axis, and that's -1, 0. So I also get embraces the number -1. Okay, so that's where this is going to get slightly weird, is we're going to get some slightly odd answers because of these asymptotes and things like that. Okay, so that's the idea. So that's the answer to the first one. So the second one, we do the same thing. So I graph x squared plus 1 over 5 minus x squared. Okay, and we can already see from the graph that there's nowhere that it touches the x-axis, but then we get two asymptotes. So I could draw my graph, just a little sketch of it over here. Okay, so in this case, we get two vertical asymptotes. And then the graph looks like this. So I was below the x-axis over here, above it in the middle, and below it over here. And in this case, same ideas as before. Greater than 0 is above the x-axis, equal 0 is on it, and less than 0 is below the x-axis. So here we want to be less than 0, so we're looking at these two pieces. So we're going to get negative infinity to something, union something to infinity. And now if I go back to my graph and I try to use the points to figure that out, notice this is 2 and increasing, right? Right now it's 2.054 and it's going up. Over here I get 2.5 something and it's going down. So I'm getting decimals somewhere between 2 and 3. But I can't know what those values are, right? So I'm not approaching an integer like I was on the previous one. So the way we find out what those values are is we set the denominator equal to 0 and we solve, right? So subtract 5 from both, add x squared to both sides, and we get 5 equals x squared. Use the square root property, and you get plus or minus the square root of 5, which is not a rational number, so that's what we have to use. So this will be negative square root of 5 over here, and this will be positive square root of 5 over here. So that's the idea. So go ahead and take a moment, pause the video, and when you're ready, press play again, and we'll go through these together. Okay, so now that you've had a chance to try these, let's go ahead and let's just start by graphing both of them in our calculator, and then we'll go from there. So the first one is negative 5 divided by, I already forgot what the first one, x squared minus x minus 6. Okay, so that was the, let me just check to make sure I got that right. Yeah, that was the first one. And then the second one is x plus 3 divided by x plus 5. Okay, so if we start with this first one, we can see that there's nowhere that the graph equals 0. And we can see that the vertical asymptote on the left-hand side, this is going as negative 1.88 and going towards negative 2. And this one is negative 2.218, and it's going towards negative 2. So the vertical asymptote on that side is negative 2. This one is 2.859 and going up. This one is 3.183 and going down, so those are approaching 3. For the other one, we can see that there's a vertical asymptote at negative 5, and we can see that there is an x-intercept at negative 3. Okay, so let's go ahead and transfer both of those graphs over here into our notes. So for this one, we had a vertical asymptote at negative 2 and a vertical asymptote at 3. And then the graph looked like this. Okay, and for the other one, we had a vertical asymptote at negative 5 and an x-intercept at negative 3, 0. And the graph looked like this. Okay. So for the first one, we want to be greater than 0, so we're just looking for the piece that's above the x-axis, and so that's that piece in the middle. So this is just going to be negative 2 to 3, right? That's where that piece is. And then for this one, we want, where is the graph less than or equal to 0? Well, that's the piece where it's below, which is this piece in the middle here. And it's between negative 5 and negative 3. We do not include negative 5 because it's an asymptote, so I put a parenthesis, but we do include negative 3 because it's or equal to. And that's an x-intercept. So x-intercepts get a bracket or parenthesis based on if we're including 0 or not. Asymptotes always get a parenthesis. Okay, so that's the idea of how we can solve inequalities, rational inequalities, using our graphing calculators. So the next thing we'd like to be able to do is we'd like to be able to find the equations of rational functions given their graphs. So instead of giving you the graph here, I've given you some information about the graph. Okay, and the way this is going to work is, let's read through the information and then we're going to apply it based on what we know about asymptotes. So a rational function that passes through 0, 1, and 2, negative 1 has x-axis as a horizontal asymptote and has two vertical asymptotes, x equals 3 and x equals negative 3. So let's start with this information because we know what that says about the denominator, right? Q of x, the vertical asymptotes are where Q of x is equal to 0. So vertical asymptotes happen when Q of x equals 0. So what I have is I know that x equals 3 and x equals negative 3, and we can work backwards to find Q of x. So first of all, I want to make each one of these equal 0. So this would be x minus 3 equals 0 and x plus 3 equals 0. And then I want to multiply those together to get q of x. So q of x is going to equal x minus 3 times x plus 3. So q of x equals, and if I multiply those together, I get x squared minus 9. So that means f of x is going to equal p of x divided by x squared minus 9. Now, we know, okay, so then the next piece of information is that the x-axis is a horizontal asymptote. So that means that the degree, because of that, we know the degree of p of x has to be less than the degree of q of x, right? That's what it said when we were talking about asymptotes. So degree of p of x is 2, which means the degree of p of x is 0 or 1. So a 0 or 1 degree polynomial looks like this. So p of x has to be linear, ax plus b. So now that we know that, we can take our f of x equals ax plus b over x squared plus minus 9. And we can substitute it in our points 0, 1, and 2, 1 to figure out what a and b are. So if I substitute in 0, 1 to start out with, so f of x is 1 and x is 0. So that would be b over negative 9 equals 1. Multiply both sides by negative 9, so negative 9 equals b. So this is f of x equals ax minus 9 over x squared minus 9. And now we can plug in the other point. So f of x is 1, but x is 2. So a times 2 minus 9 over 2 squared minus 9. So that's 1 equals 2a minus 9 over negative 5. So negative 5 equals 2a minus 9. Add 9 to both sides, and you get 4 equals 2a. Divide by 2, and a equals 2. So that means that our final answer is f of x equals 2x minus 9 over x squared minus 9. Okay, so that's the idea. So you start by working backwards. The vertical asymptotes tell you what the bottom has to be. The horizontal asymptote tells you how the top and the bottom are related. And then you can use the points to find out the coefficients of the top. So let's go ahead and try another one here. So the second one here says that we have a rational function that passes through negative 1, 2, and has the line y equals negative 2 as a horizontal asymptote, and it has the line x equals negative 3 as its only vertical asymptote. So we'll start with the vertical asymptote part. So that means we take x equals negative 3. We set that equal to 0, so add 3 to both sides, so x plus 3 equals 0. And so that is my q of x. So that means f of x equals p of x over x plus 3. Then the next thing we can do is we can use the fact that y equals negative 2 is a horizontal asymptote. So the fact that it's a horizontal asymptote means the degree of p of x has to equal the degree of q of x. Okay. And in this case, the degree of q of x is 1, so the degree of p of x also has to be 1. So that means p of x is linear again. So that's ax plus b. Okay, because x to the first power. So our f of x. And then the other thing we know is we know that the horizontal asymptote is equal to negative 2. Well, remember, the way we found horizontal asymptotes is by taking the leading term of the top divided by the leading term of the bottom. And that, in this case, has to give us negative 2. X divided by x cancel, so I get a equals negative 2. So f of x equals negative 2x plus b over x plus 3. And so now we can use the last piece of information we have, which is it goes through the point negative 2, 1, 2. So f of x is 2, y is 2, so that's f of x, and x is negative 1. and we simplify. So this would be 2 plus b over 2. Multiply both sides by 2 to get 4 equals 2 plus b. Subtract 2 from both sides to get 2 equals b. So our final answer here is f of x equals negative 2x plus 2 over x plus 3. Okay, and so that's the idea. So at this point, if you want to, you can go ahead and pause the video, and then we'll go, once you're ready, you can start it again, and we'll go through these together. Okay, so let's go through them together. So start with the vertical asymptote, which in this case we have x equals 3. So x equals 3, set one side equal to 0, so x minus 3 equals 0. So q of x is x minus 3. So that's our f of x now. We know what the bottom is, but we don't know what the top is, so p of x over x minus 3. So now we can use the fact that it has the x-axis as a horizontal asymptote. So the degree of p of x has to be less than the degree of q of x for the x-axis to be a horizontal asymptote. The degree of q of x is 1, so that means the degree of p of x has to be 0, because that's the only whole number less than 1. So that means p of x is simply a constant, so we'll call that b. So f of x is equal to b over x minus 3, and now we can plug in the point to figure out what b is. So this will be y is 4, so 4 equals b over 0 minus 3. So that's 4 equals b over negative 3. Multiply both sides by negative 3 to get negative 12 equals b. So f of x equals negative 12 over x minus 3. And then the last one, start out using the vertical asymptote again. So x equals 2. Set one side equals 0, so subtract 2 from both sides. So x minus 2 equals 0. So q of x is x minus 2. So the bottom of our rational function is x minus 2. Now it tells us in the next part that we have a horizontal, y equals 1 is a horizontal asymptote, so that means the degree of p of x has to equal the degree of q of x. Degree of q of x is 1, so the degree of p of x has to be 1. So f of x equals ax plus b over x minus 2. Actually, sorry, let me do it more similar to what we did up above. So that means p of x has to equal ax plus b, and we know what that has to be, so we take ax divided by x, and that has to equal 1. So in this case, a is 1. So f of x is x plus b over x minus 2. And now we can use the point. So y is 5, x is 0, so 0 plus b over 0 minus 2. So 5 equals b over negative 2. Multiply both sides by negative 2, and b is negative 10. So this will be f of x equals x minus 10 over x minus 2. Okay, so that's how you can use the graph or information about the graph of a rational function to find the equation of that rational function. The last thing in this section is application problems with this idea of rational functions. So let's look at a couple examples with that, and then we'll be done with this lecture video. So the cost of renting a car for one day is $39 plus 30 cents per mile. Write the average cost per mile C as a function of the number of miles driven in one day. Graph the function for x greater than 0. What happens to C as the number of miles gets very large? So we can start out by writing a function for cost. So C of x, well, we want to find average cost here. So let's go ahead. So the average cost per mile is simply going to be the cost divided by the number of miles. So C of X, so the cost is $39 plus 30 cents per mile, which is 0.3x, divided by the number of miles. So this is 39 plus 0.3x over x. So if I graph that, 39 plus 0.3x over x. So if we look over here and we just look at what happens as x increases, what we'll notice is the cost is going down, okay, over the long term, right? It keeps getting smaller. As x gets bigger, the y values right now, it's at 86.5 cents, and it's going to keep getting smaller and smaller and smaller. Will the average cost ever get to zero? No, right? Because it's average cost. You're always going to owe at least some money if you rent this car. So the idea here is, well, what happens to this as we get close to zero? Well, that's basically asking you to find the horizontal asymptote. So to find the horizontal asymptote, we can notice here that the degrees are the same, and these are the two leading coefficients. So our horizontal asymptote is going to be at 0.3x over x, which is 0.3. So y equals 0.3. So what happens is the number of miles gets very large. Well, what happens is the cost per mile, the average cost of renting the car becomes the same as the cost per mile. So if you drove this car for a long time, for a lot of miles, the initial $39 in the long run doesn't matter. It's just costing you 39 cents per mile. Okay, so that's the idea. So another similar one says, Winona paid $100 for a lifetime membership to Friends of the Zoo so that she could gain attendance to the zoo for only $1 per visit. Write Winona's average cost C as a function of the number of visits when she has visited X times. Okay, so this one's very similar to above. Her cost to go to the zoo is the $100 she paid up front plus $1 for each visit. And her average cost then is that cost, total cost, divided by the number of visits she makes. So what would her average cost be per visit be when she has visited the zoo 100 times? Well, that's just C of 100. So that's 100 plus 1 times 100 over 100. So that would be $200. $2. It would be $200, 200 divided by 100, which is $2. So she would be paying $2 per visit after she's gone 100 times. And if we look at this graph, the graph of this one would look pretty similar to the one above. What's going to happen if she bought this when she was young and she visits the zoo every day? So in other words, what happens if she goes to the zoo a lot? Well, the same thing's going to happen here that happened above. This 100 is going to go away, and I'm basically going to find the horizontal asymptote, which in this case is y equals 1x over x, so y equals 1. So as x gets really, really big, her average cost goes to $1 per visit. Okay? And so that's the idea of how this can be applied. So that's it for our lecture video today. Make sure you're keeping up with all the assignments on my math lab. And as always, if you have any questions, feel free to email, call, or text.